So I'm Aikaterini from the Valencia node, and I will be presenting you some of our tools for tumors and lesions segmentations. So these are the contents, a very quick introduction on who we are and what a segmentation is, even though the previous actual speaker did talk about segmentations, and then we will move straight to the segmentation tools. So we are a medical image analysis group directed by the Dr. and Professor Luis Martí Bonmatí. And some of the main tasks that we perform on our daily practice are data extraction, standardization, anonymization, as well as image preprocessing analysis and artificial intelligence algorithms. So we participate in various international, national, and own projects. And here you can see some of that, like the biggest one, let's say. So these are the most typical imaging modalities. I believe that most of you have undergone at least one, probably X-ray or MRI. So these are different technologies. They are used to highlight different structures, to evaluate different pathologies. They have their pros and cons, but what they all have in common is actually the image. So when we undergo a study to, let's say, investigate whether or not we have a tumor, inevitably, we will not just see the tumor, but the surrounding area as well. So the first step that the radiologist would do would be to manually delineate the region of interest, in this case, the tumor. And this way, they can better characterize the substrate and track temporal changes. But this is not only helpful for the radiologists, but for us, investigators as well, because image segmentation is the first step in the development of diagnostics tools, as well as the extraction of imaging biomarkers. So this radiology segmentation is actually a manual segmentation, and it is the gold standard because it is really robust. It's performed actually by an expert, but at the same time, it's quite time consuming. And this is why we have many solutions for automatic segmentation. So in this case, we train a neural network or a registered software, and we acquire automatic segmentation masks, which is really, really quick. But in some cases, it's not as robust as the manual segmentations. And this is why we many times opt for an in-between solution, the semi-automatic segmentation. So this way we have the best of both worlds. First, we train a network and extract a completely automatic segmentation mask. And then we ask a radiologist to have a look at this mask, and if any corrections are needed, to do them manually. So it is really quick, not as quick as the automatic segmentation, because it requires some interventions from the specialist, but not as slow as the manual one, but it is as robust as the manual one. So this is a quick disclaimer. I will be showing you some of our segmentation tools that extract automatic masks. So we use them for investigation purposes so far, and they could be actually implemented into the clinical practice, but at their current state, they do require this inspection from the radiologists. So the basic architecture that we use for our tools is a UNet. I believe that many of you know what a UNet is. For those who don't, a UNet is a neural network that follows a U architecture, hence UNet. So it is composed of two main parts. The first part, which is the encoder part, this consists of various convolutional layers followed by activations and pulling operations to downsample. And then we have the second part, which is the exact opposite, the decoder part. So here we have deconvolutional, and we also have activations and upsampling operations. And not only is it, let's say, the exact opposite, but it is a mirror of the encoder. So each layer of the encoder has its negative layer on the decoder. And what makes this architecture so unique is actually the use of skip connections that directly feed the output of its encoder layer to the negative decoder layer, making sure that we do not lose these fine-grained details that are so important in medical imaging. So with all this introduction, let's move to our first tool. So this tool is in order to segment glioblastoma tumor lesions, and operates in MRIs. So this is not a public tool yet, but we do have an article published describing the entire procedure. So there are two main novelties in let's say, this solution with respect to the state of the art. The first one is that, like normally in brain cancer, we have various regions of the tumor and we perform multi-region segmentations. But in this case, we trained 4 different models. And so each model actually outputs a binary mask, and then we join all of them to be left with a multi-region mask. And the second one is actually the architecture itself, which some of our developers developed from scratch. So this is a UNet-like architecture with the difference of the addition of residual blocks after its convolutional and deconvolutional layers. So here, let's see, no, sorry. Let's see if I can do it. I cannot. Anyways, so here you can see how residual block looks like. So it consists of various layers of convolutional, normalization, and activation functions. And then we have also skip connections within each residual block. And this makes sure that each convolutional layer actually learns the residuals between the input and the output. And we ensure a more stable training and more precision in the segmentation. So in order to train this model, we used an external public dataset, the BRADS dataset, and we performed an 80-20 split. And then in order for the outer test, we used 50 glioblastoma images from our hospital. And as inputs, we use T1 with contrast, T2, and flare. So we performed a typical preprocessing, denoising, bias-fold correction, skull stripping, voxel resampling. And then we didn't fit the entire image, but we performed some crops on the voxels, and we made sure that 2 successive patches had at least 50% overlap. And depending on the area, we use different input sequences. For example, for necrosis, we use T1, but for edema, we use T1, T2, and flare. And here you can see the results on the left. We see the results on the internal segmentation, and on the right on the external. So I'm sorry, I don't have a mouse with me, so it's a little bit difficult to handle this. So here are the recall actually. So we can see that for the internal results, the edema and the enhancing tumor were very well segmented, but the algorithm tended to confuse a little bit the necrosis with edema. So in the images below, the necrosis is the red one and the edema is the green one. But for the external test set, we can see that all 3 areas, necrosis, edema, and enhancing tumor, had some voxels confused as background. So this was the difference, but overall, we had really good segmentations, and this is described in detail in the article. So moving to our second tool, this is for segmentation of glioma tumor lesions. So glioma is one of the most aggressive forms of brain cancer. And we have this code, the code of this work actually open in the Bitbucket. And we also have a pending paper, which is currently under revision and hopefully it will soon be published. So here we use the same architecture as before, the UNet-like with the residual blocks. And we used 70 MRI images from 52 patients. We performed an 80-20 split with the 20 being the holdout set. And here we used very small voxels, voxel patches actually. And we trained 3 different models. The first one only had inputs, the voxel patches of the T1 images. The second one had inputs, the voxel patches of the flare. And if we didn't have flare, we used the T2 images. And then we trained a third model that actually registered the T1 to the T2, and then we had overlapping patches of the T1 and the T2. So here you can see the results of the 3 models. All of them actually performed really good. But the last one, the combined T1, T2 patches, were the ones that performed the best with a DICE score of 0.88. Now moving to our next tool. So here we move from the brain to the spinal cord and neuroblastoma. And also the code of this tool is open to public in GitHub. And we have actually two publications linked to this work. The first one is the one that you see here. And the second one, you will see 2 slides apart. So for this work, we used 3D NN-UNet. And we used data from 3 different centers across Europe, Spain, Italy, and Austria. But the objective of this work was actually twofold. On the one hand was to develop a neuroblastoma tumor segmentation tool. And on the other hand was to study the inter-observer variability at the time of the segmentation, and also the variability between the automatic masks and the masks from the radiologists. So we used 132 neuroblastoma MRIs, and we made actually a radiologist segment all of them manually, and we made a second radiologist segment just a portion of them. So this way we studied the inter-observer variability. And then for the training of the model, we split as always to a tuning and validation set. And for the training, we use a 5-fold cross-validation, and we actually leveraged the outputs of all 5 folds and created an ensemble model in order to create the final segmentation masks. So this way we were able to achieve a more reliable, more robust, and better performing segmentation masks. Here you can see the DICE score across the 5 folds, as well as the DICE score at the validation states. So you can see that comparing the validation states with the 5 folds, we see less variability in the validation states in most of the cases. And we also see a higher DICE score. So all of them actually show very high DICE score between 0.87 and 92, but the validation one is the best one. So this is our second article linked to this work. And here you can see just some, just for visual, for illustration purposes, we put some example of some segmentations and the respective DICE score. Now we move to breast cancer and mammographies. So this is a work in progress, actually. So we don't have the code public yet. So in order to train our model here, we actually used a huge database from 9 different public repositories. So we were left with really hundreds of thousands of mammographies, bilateral, and we inspected them visually and chose around 10,000 of them. So the criteria were to have a biopsy-proven anomaly and the respective segmentation mask. We performed typical pre-processing, and then we used these 10,000 images to train our network with 5-fold cross-validation. And then for an external test set, we used the mammographies of our hospital. So we used 400 mammographies and the respective segmentations of trained radiologists. So here we do not have a full volume. We are in mammographies which are actually a form of X-ray, so we'll have just 1 image. And this is why we trained in 2D NN-UNet. And here you can see the results. So we have a mean DICE score of 0.83 so far. So we're still working on that, and hopefully we will get better results. And last but not least, we move to the segmentation tool for prostate tumors. So this, we go back to the MRI, and this is also work in progress, so it's not public yet. Here we followed slightly different, let's say, procedure. So we wanted to extract lesion masks, but we leveraged gland masks in the first place. We used around 1,000 biparametric MRIs from the PK dataset, which is a public dataset, and the respective masks. And we used 3D NN-UNet. So we used the entire dataset without any split in order to pre-train the UNet. And then we used 158 biparametric MRIs and the respective lesion masks from our hospital. and used the weights from the pre-trained architecture in order to fine-tune our model, and this way extract the lesion masks. So here you can see the results across the 5 folds and the mean die-score. We have a mean die-score of 0.54, which I know that doesn't seem so promising, but considering the state of the art in lesion masks in prostate cancer, it is actually really good. And you can see also how the dye varies across the ISAP grades. So the ISAP grade is actually a way to measure the aggressiveness in prostate cancer, and the higher the grade, so the higher the aggressiveness. So we see that we have better results with more aggressive cases, which makes sense because we have a bigger tumor. Besides the most aggressive case, where we observe a drop in the performance, but this is probably because prostate cancer tends to be, let's say, detected in the first stages. So we didn't have as many MRIs of ISAP grade 5 as we would like to. And probably this is why we have a drop in the performance. So this was everything from my side. And instead of conclusions, I would just like to leave a picture of my group, because this is a collaborative work, and I would like to thank them and you for your attention.